Okay, so this is what's going to happen. This is our objective for today. You're going to describe two types of error that can happen when you're testing a hypothesis using type 1 and type 2 error definitions in order to explain how the variation in a sample can confuse the results of an inference. Okay, so let me try to explain a little bit of what's going on here because it's not necessarily obvious. So if you think about what's going on in the greater scheme of things here, you are taking a sample, which is part of the population. And you are making an inference about the population, which is the whole. Okay? So, give me 1 second. Trying to help tech understand what's going on. All right, so you're taking a sample, you are making an inference about the whole population. All right, so here's the problem. This is incomplete information, right? And the language that we've been using here is that you have a degree of confidence. So we've said that you could create a 95% confidence interval, which we said was the same as doing a hypothesis test with alpha at 0.05, right? So this alpha is the probability that I'm wrong in a particular way, and this is the probability that I am right. These two things are interchangeable. Now, the question first is like, what's the source of me not being 100% sure? And what's going on here is there's what's called variability in samples. Could I take a simple random sample of Garrison Forest School students of 20 people and happen to get the 20 tallest students? It's possible, right? If it's a simple random sample, it is possible. Is it likely? No. But it is possible because every subset of 20 has an equal probability of being chosen. So it's possible that I could grab the 20 tallest students. It's also possible that I could grab the 20 smallest students. Now, if I happen to grab the sample that had the largest, the 20 tallest students, and drew an inference about the average height of a Garrison Forest School student, what would I think about the height? Yeah, the average height would be really high, right? It would be pretty tall. And if I grabbed that subset and I made an interval around what I thought the height would be, it probably wouldn't actually have the average height of the student for Garrison Forest in it. It would miss. Yes? Correct. So there could be like some sort of variation here, right? And if I grabbed like the sample that was all small, short people, I would think that like we're all short. And that sample would miss. So the question here is like out of all the possible samples of 20 people that I could grab for Garrison Forest School, if I make the interval around the mean of that sample a certain size, then 95% of those samples will have the true mean in it. 5% of them will not. That's what I mean by my degree of confidence. That if I took this sample from that population and made its interval a certain size, then 95% of the time I'm going to have the true mean in that interval. Now, that's a risk I take. That's part of statistics. You don't ever get an absolute answer. You can get it to a high degree of confidence. If I'm 95% sure that the true mean is on that interval, I'm feeling pretty good about it. But I'm still not 100% sure. And the only way I can be 100% sure is just to keep making the interval bigger and bigger and bigger. Like if I said, hey, people are between, the true mean of the height of a Garrison Forest student is between 0 and infinitely many inches tall, then I get 100% degree of confidence. Because yes, the true mean of your reality is somewhere between 0 and infinity. But that doesn't tell me much. It's not very useful. So I do have to allow for error. Now, there are two types of error. Okay, so like if you go back into the notes on this from last time around, it does a pretty good job of explaining these two types of error. There we go. Hi. I'm kind of in the middle of teaching right now. So I've got a workaround that's going to go for this period. But here's where I am. Let me pause this because they don't need to see this. All right, so I was going into trying to show you where, like, in the notes from last time around, there's two types of error, okay? And the alpha is rejecting the null when it's true. The beta, or the type 2 error, is the probability that you fail to reject the null when it's false. All right, so the big key here is that in order to get a type 1 error, okay, which is the more common one, the one that we most worry about, the type 1 error is that the null hypothesis H null starts off as true, is actually true. And the test says it's false. So this is what we are calling alpha here. That's the probability of the type 1 error, is that the null hypothesis is true and the test actually says it's going to be false. Okay, type 2 is the other way around. All right, so type 2 is that H null is false and the test says it's true. So here we're rejecting a true null hypothesis. Here we're failing to reject a false one. Okay? Which one is the worst case? Usually rejecting the true one is the worst situation. Okay? If the null is true and we reject it, that's usually the situation where it's worst case. The other one is, the other way around. So like the one that I like to point out is, like, if you were to do like weather prediction, they would make the H null, it's gonna snow. And the H alternate being it's not. Okay? So what would make the null hypothesis true here is that it actually snows, right? So it snows. What would be the type 1 error? would be that the weatherman would say that it's not going to snow. So the weatherman's going to say sunny and 40, right? And that it snows and it's 28. That's the type 1 error for that situation. Now, weather forecasting is actually set up in this model, where the null hypothesis is the storm and the alternate is the not the storm. So what they are trying to reduce is the alpha. They want to make it really, really, really low so that if there is the chance of a storm, they're predicting it. Yes? It's not so simple as that. The 95%, so if it snows, right? So let's say it actually snows, right? That's what actually happens. Then there is a 95% chance that we got it right. Okay? And there's a 5% chance that we got it wrong. So the 95 is we made the correct prediction, the 5% is we made the wrong prediction. So this is my confidence level, the percent chance that I'm getting it right. This is the percentage chance of a type 1 error. Correct. That confidence level always deals with the null hypothesis. Now, here's the type 2. The type 2 error in this case would be that the null was false, right? So the null said it's going to snow. The false would be that it didn't snow, right? So the type 2 error in this case would be it didn't snow. But we predicted the storm. Okay? So the type 2 error is that it didn't snow, but we got the prediction wrong. So to have an error, you always get it wrong. Type 1 is that you reject the null when you should have kept it, right? Type 2 is that you kept the null when you should have rejected it. In most situations, you set it up so that the type 2 error is not as bad. So this is why this one gets called the alpha. Like, it's the more important one, and this is what we call beta. So most tests are set up to try to minimize alpha first, and then to try to minimize the beta if you can. The alpha and the beta are oftentimes independent. If you remember back in class, we talked the thing about Bayes' theorem and how they're related slightly through the sample size. But the alpha is one end of the Bayes' theorem, the beta is the other. If you think about this, like, think about like something like the vaccine trials, right? The big issue is side effects. Right? So if they're looking at a particular side effect, the null hypothesis would be that you don't get the side effect, right? And the alpha would be the probability that you get the side effect when you're predicted not to. Okay? That's what we want to avoid, is people getting the side effect when they're expecting not to be getting it. So when they say something like, X number of people get the side or have the side effect, that's what they're talking about. That percentage is the alpha, the type 1 error in that situation. Now, this is overly complicated and doesn't need to be that way. So I'm going to drive into Schoology here. Okay, so that 2% is the error. So that would be, they're 98% confident that somebody's not going to get side effects. It would a 2% error, okay? So the statement is, think about it this way, you try to build a vaccine. where the null hypothesis is if I get the vaccine, that I don't get the side effect. Okay? Because if the null hypothesis was if I get the vaccine, then I'm going to get the side effect, then we shouldn't be accepting that vaccine. It's more likely that you don't. I mean, now, like what we're finding with like the current vaccine is that people are having the number of people that are getting a side effect, a 1-day side effect from the second dose of the vaccine is pretty high. Like I went through it. Like I had one really bad day in my life. Now the question is like, okay, even though that type 1 error is pretty high, because it's probably somewhere in like the 15 to 20%, because as far as I'm reading, like 1 in 5 people are probably experiencing it. Is the side effect so bad that you don't get the vaccine? Like a day worth the chills and not feeling good is okay for me not to actually have COVID. Does that make sense? Like, I have to admit, during the day, all I wanted to do was find a knob to turn down the sun because it was too bright. Okay? It was awful, but that's livable. Now, if the side effect is something like blindness, death, that would be a pretty bad side effect, ongoing brain deterioration, something like that, I'd probably want a much lower alpha on a side effect like that. Side effect like nausea, not so bad for a one-off vaccine, but a side effect for like, what's the word I want to use? Something like nausea on a pill that you have to take every day, that would be awful. You know, if like 16% of the people who take this medication get nauseous every time they take it, and this is a therapeutic drug that you have to take day in and day out, that's way too high. That's an unacceptable alpha, if that makes sense. Okay. Oh, okay, I can fix that. Technology is wonderful when it works. All right, so if you refresh it, it should come up. All right, so what I did in the problems here is I kind of walked through the process of trying to understand what's happening. All right, so, all right, so let's roll up a little bit here. All right, so the first one says the claim. The proportion of people who write with their left hand is equal to 0.1. All right, so the first one is like very familiar. Write the null hypothesis, write the alternate, right? This is a claim about the proportion, so it's a P, and it is 0.1, and it's an equivalent. It is equal to 0.1, so we're going to make it not equal to 0.1, right? And that's like what we've always been doing, right? So now the question is like, describe the type 1 error that could result in this test in terms of the claim. So in order to have a type 1 error, you have to have the null hypothesis be true, okay? So in reality, 10% of people write with their left hand. And what does the test say here? The test says so start with this. The type 1 error is that the null hypothesis is true. So that's why I wrote this. That the null hypothesis says that 10% of people are left-handed. Fair enough? So in reality, 10% of the people who write with their left hand, The test says that this is false. So that's the type 1 error. The reality is 10% of the people are left-handed. The test tells me otherwise. Now, the type 2 error, which is part C here, is in reality the portion of people who write with their left hand is not 10%, right? Because that statement would say that the null hypothesis is false, right? The null hypothesis says that the proportion is 10%. So in reality, the proportion of people who write with their left hand is not 10%, but the test does what? Says it is. So all I'm doing is I'm just identifying what are the two errors. Okay? I don't have any data to test this on. Okay? I'm just saying that if I conducted this test, these are the two ways I could get it wrong. The type 1 error is that 10% of the people are left-handed and the test says it's wrong. The type 2 error would be that the proportion is not 10% and the test says it is. Does that make sense? We don't know which of those errors is happening, and even if any of those errors are happening. All right? So the second one follows very similarly to this one. I want to drop down to the third claim here because it's a little different. Okay? Because you got to kind of think through what's going on here. In this third claim, it says the proportion of female statistics students is greater than half. So I have to, like for G here, I have to write out the two hypotheses. But the problem here is that this is a greater than, right? So that's going to be the one down here. My claim is down here, right? The null hypothesis is that the proportion is half. Are you with me there? All right. So this is not so bad, though, because you ignore this, okay? Whenever you're doing type 1 and type 2 error, all that matters is the null hypothesis. That's it. Okay? So the type 1, H, here, is going to be the proportion of female stat students is 50%, and the test says it's not. Right? That would be the type 1 error. So you actually ignore the claim, you ignore the alternate hypothesis, you just work off the main hypothesis. B, or HI, the proportion of female stat students is not 50%, and the test says it is. Now, why do I not deal with the greater than? Because the test itself is a one-tailed test. The only way that that test is going to pick up that it's not 50% is that the proportion would be greater. Does that make sense? Because I'm only testing that end of the tail. But that doesn't come into my description of type 1 and type 2 errors. So it's all based on the null hypothesis. You don't have to look at the alternate hypothesis. Once you have the null, you can base everything off of that. Say that one more time. The null isn't, but the test that's performed, the test that this is talking about, is using these two hypotheses in a set of data. When you use these two hypotheses in a set of data, you're using the greater than. When you throw that in the calculator, you're going to pick the greater than, which is going to give you a p-value based on that, which means that if my p is going to be smaller than my alpha, which is where I'm rejecting the null, then the proportion is going to be bigger than 50%, because it's the only way I can get a p that's smaller. That's two-tail. So the alpha could be on either side of that one. So like when you get the type 1 error there, it could be either to the left or to the right. Here, it's only going to be to the right because it's a type 2 test. But when you're describing the error, you don't need to account for that because it gets picked up in the test. By simply saying the test says, it's accounting for the fact that it's going to be to the right. Okay? So I think I gave you 4 all total. I've done 1 and 3. I'm going to give you a few minutes to try numbers 2 and 4, and then we'll come back and we'll talk some more. I'm going to pause this. Okay, so let's take a look at where this is and try to make sense of it, right? So the third claim is the proportion of gamblers who consistently win in casinos is really, really tiny, right? So it's that 1 in 1,000, right? So H null is that the proportion, is D, is equal to 0.001, right? HA is that the P is not that, because this is a claim of equality. So the error here is that the proportion of winners is 0.001, and the test what? Says it's not. And I'm not good with words. Okay, great. F, the proportion of winners is not 0.001, and the test says it is. That up. Does that make sense? Are we in agreement on that one? Pretty good? All right, so let's drive down to the last one here. So the proportion of husbands that are taller than their wives is less than 90%. All right, so H null. The proportion would be 90%, right? And the alternate is that the proportion is less than 90%. So that's J. Okay. So if H null is true, then how can I write this in a clever way? I could say that 90% of husbands are taller than their wives. And test says they're not. Or that the proportion, that's not correct. The proportion is not 90%. And then L, the proportion of husbands that are taller than their wives is not 90%, but the test says they are. Yeah? We're okay with that? Do you buy that one? 90% of husbands are taller than their wives? 90 feels a little big. I gotta be honest with you on that one. I'm taller than my wife by half an inch. I'm like 5'9". She's like 5'8.5". She wears big shoes. I'm shorter. It's funny. Yeah, it's like pretty wild. I think that you could do a study, and I bet you would find that there's probably something here, and there's probably something about heights being comparable. I wonder if there's anything to that. But people do weird things when they pick other people to be around. So I don't know how that happens. All right, so it's 11:21. We have gotten through the glitchiness. I will post this for the folks that have not been able to get in on Zoom, and we'll go from there. All right, this is the last topic in this unit, okay? So we're going to start into an assessment cycle here. That will be not on this quarter, though, okay? So that's where we are.